thank you very much for this very prestigious award. I'm really honored. I'm a physicist, a particle physicist, and I will try to explain what that means. But I study humanities at high school, what we call Liceo Classico in Italy, and also have a degree of piano degree from the Conservatory in Milan. So I'm very happy to be here with the representative of academies of sciences and humanities, because both are very close to my heart. So I'm also very happy to have the opportunity to take part in this panel. And also thank you for allowing me to share my some thoughts on the theme of the panel, European research collaboration in a shifting geopolitical landscape. And I will do so by bringing the example of CERN, the European Laboratory for Particle Physics. And also we'll try to underline the values of CERN. Professor Loprieno already anticipated this, and it's really interesting that I have a final slide on the values, which are European values, whatever this means, as Professor Loprieno just said. But before talking about CERN, let me introduce Aeroforum. CERN is not unique in the landscape of international scientific organization in Europe. Aeroforum is a consortium which brings together 8 large European intergovernmental scientific research organizations. Let me move somewhere else because I can't see the slides. Let me go there. So these 8 large European international scientific research organizations are listed here. They include ESA, the European Space Agency, EMBL, the European Molecular Biology Laboratory, CERN itself, ESO, the European Southern Observatory, the European XFL, the Free Electron Laser in Hamburg, the ILL Neutron Facility in Grenoble, the European Synchrotron Radiation Facility also in Grenoble, and Eurofusion. This research organization work over physical scales that span from astronomical distances to particle physics. So it's really a span orders of magnitude in terms of scales. I think it's important also with a view to our discussion in the panel to maybe go through the commonalities and the values of these organizations. First of all, they provide world-class research facilities in their respective fields. So they do excellent science. And therefore, they attract a huge community, in total 100,000 users from Europe and beyond. Actually, they are European organizations, but they are leaders in the world. For this reason, because they have a huge community, international communities, they foster collaboration across borders. They are based on intergovernmental treaties or convention among member states. The member states share the cost of the facility. This is public funding, public money. Non-member states contribute to projects a la carte, so they put money in the project they are interested in. This funding model has been the real success for this organization because the fact that they bring together funding and contribution, also human resources from various member states in Europe, allows them to carry out projects that no single country could carry out alone, but also it provides long-term budget stability, which is absolutely crucial because in most cases, the projects carried out by this organization are long-term, the last decades. And so only this budget stability in the case of CERN is 70 years of history has allowed this organization to become world leader. They are governed by a council, projects are peer-reviewed by independent international experts, so high scientific level. And to stay at the forefront of research, they need state-of-the-art instruments, and so they develop cutting-edge technologies with huge impact on society. We will see the example of CERN. Training of the future generation is also part of their core missions. They foster open science, so science available to everyone, open data, open software, open hardware, and they have an important socioeconomic impact directly through the science they do, or as a consequence of knowledge transfer, industrial return, the education and the training of world-class generation of young people that then go to work in other fields of society. So I think these are very important elements to keep in mind when we also discuss about the excellence of European science. So let me now take the example of CERN, and I will underline some aspects that are important for later on for the discussion in the panel. CERN mission rests on 4 pillars: research, collaboration, global collaboration, technology and innovation and transfer to society, and education and training. And I will go through these pillars one by one with a little bit of physics, but very simple and very short, and then maybe underline more the collaboration part. So, CERN is the biggest laboratory in the world for particle physics, and particle physics is the most fundamental of all sciences because it studies the smallest constituent of matter and of the universe. We call them elementary particles because they cannot be cut into smaller pieces. This aerial view of the Geneva region shows here in red the border between France on the top of the screen and Switzerland. In the lower part you see Geneva Airport, Lac Léman, the Geneva Lake, and this circle here shows the position of the Large Hadron Collider. It's a 27-kilometer ring, 100-meter underground. It hosts the most powerful accelerator ever built by humanity. So what is particle physics? As I said, particle physics studies the smallest constituent of matter. So we all know that matter is made of atoms. Atoms, despite the names, they are not elementary. They are made of a central nucleus surrounded by a cloud of electrons. Nuclei are not elementary particles. They are made of protons and neutrons. And protons and neutrons are not elementary. They have substructure that are called the quarks. And as far as we know today, quarks and electrons are elementary particles. They cannot be cut into smaller pieces, and therefore they are the fundamental constituents of matter. You know, these chairs, all of us in this room, even Professor Loprieno is made of electrons and quarks. We are all made of electrons and quarks. The visible universe is made of electrons and quarks. So physics at CERN, at the Large Hadron Collider, allows us to study matter at the level of the quarks. So on physical scales of smaller than a billions of a meter. So you should consider this big accelerator like giant microscope. If you want to study human cells, a tabletop microscope is okay in a lab. But if you want to study matter at the level of the most elementary constituents on these physical scales, you need a lot of energy. You need an accelerator. So this is really the ultimate microscope that humanity can build. At the same time, the study of the very, very small allows us to understand the very, very big, so the structure and the evolution of the universe. And this is because we know today, from cosmology, but also from very strong experimental evidence, that the universe had origin 13.8 billion years ago, following a big explosion called the Big Bang. And at the beginning, like in an explosion, the universe was very dense and very hot, and was essentially a gas of 3 elementary particles. With time, it expanded, like after an explosion, it expanded, it cooled down, and so the elementary particles combined with each other, first quarks to find neutrons and protons, then neutrons and protons to find nuclei, then nuclei with electrons to find atoms, so the opposite movie of this cartoon here, up to the macrostructure we know today, galaxies, stars, planets. And there are 2 complementary ways to study the universe and its evolution. One is through telescope in space or ground. The telescopes look at the macrostructure, galaxies, planets, and by looking at the farthest objects, they can go back in time. And the other complementary way, is through accelerators. Actual accelerators allow us to go much farther back in time than telescopes. They allow us, the LHC allows us to go back to 10 to the minus 12 seconds, a millions of a second after the Big Bang. What does this mean? It means that the energy that we produce in the collisions of the beams, particle beams that we accelerate, and we'll see later on how, this energy corresponds to the temperature that the universe had 10 to the minus 12 seconds after the Big Bang. And this temperature is 100,000 billion times the temperature in this room. So we are able to reproduce in a laboratory, in underground laboratory in Geneva, the very, very early universe and understand how that universe behaved. So to do this, we need a lot of technology. We need very complex instruments, big and complex instruments, particle accelerator, particle detectors, and computing infrastructure, and a large variety of cutting-edge technologies developed at CERN, from superconducting materials and magnets to electronics, cryogenic, vacuum, various instrumentation, big data, quantum, AI, and all these things. Technology that, as we will see, we transfer to society free of charge, at zero cost, with no profit. So again, this is the Large Hadron Collider. So what we do is a 27-kilometer ring. What we do is to accelerate two beams of protons in the two opposite directions, up to the highest possible energies, where the limit come from the available technology, the technology of magnets that are needed to keep these beams on a circular trajectory. So this is the limit. And we smash them at 4 points of the rings, where in 4 big underground caverns, we have installed 4 big instruments called ALICE, ATLAS, CMS, and LHCb. These are particle detectors. They surround the full, they cover this full solid angle around the collision point, and they detect all the particles produced in the collision. And they give us an image of the collision event. So if the accelerators can be seen as giant microscope to study matter at the smallest distances, particle detectors can be seen as cameras that take picture of the collision. Okay. 2 years after the start of operation in July 2012, the ATLAS and CMS experiments announced the discovery of a new and very special particle, the Higgs boson. I will say a few words later on why this particle is so important. It was a truly collaborative effort involving for decades 6,000 scientists from all over the world. So this is a spectacular image of the underground tunnel, the 27 kilometer. These blue tubes contain the single most important technological element that allow us to make a big jump in energy and therefore bring the leadership in fundamental particle physics from the United States to Europe. And these are superconducting magnets of new generation at the time. Now the technology has evolved, but they're still quite important, quite cutting edge, which were developed at CERN and then built by 3 leading industries in Europe, Alstom in France, Ansaldo in Italy, and Babcock Knoll in Germany. A fantastic example of partnership between CERN and European industry and transfer of knowledge from CERN to European industry. I said detectors are like giant cameras, but the particle beams from the LHC, from the Large Hadron Collider, collide 40 million times a second. So these cameras must be extremely fast because they have to take 40 million pictures a second. They are enormous, they are very big. ATLAS, the biggest one, is like half the Notre Dame Cathedral in Paris, but underground. But at the same time, they are very complex and very precise. They have 100 millions of sensitive elements with also silicon pixel, very, very small silicon pixels. So this really huge complexity and huge technology. Maybe I will skip the computing part in the interest of time, which is also important because the LHC computing grid paved the way to the cloud. To cloud computing is the precursor of cloud computing. I give you some more figures to impress you. So the magnet you've seen in the blue tubes are superconducting, so they work at cryogenic temperature, 1.9 Kelvin, 1.9 degrees from absolute zero, means minus 271 degrees Celsius. It's the largest cryogenic system in the world. This is colder than outer space. The beams of protons contains, when the LHC operates, 200,000 billions of protons of high energy, and so the energy stored in these beams is very large, 400 megajoule. This corresponds, I was told, to the energy of an Airbus 320 running at 110 kilometers per hour. So it's a lot of energy. So this also tells you the precision with which we have to control those beams. And the experiments have so far produced something like 1.5 exabyte of data. So these are examples. So one word on the Higgs boson, why this particle is so special. So we have discovered so far 17 elementary particles. The Higgs boson is completely different from the other 16. He has very special characteristics, we call them quantum numbers in physics. It brings a new type of interaction different from the 4 interactions we know today, gravity, electromagnetic, weak and strong. But also is related, most importantly, to the mechanism that allowed mass to form in the early universe, matter to form in the early universe, the matter of which we are made. Before the settlement of the Higgs field in the early universe, matter could not exist. So it is thanks to the Higgs field, which appeared at some point in the early universe, 10 to the minus 12 seconds after the Big Bang, we don't know why, that particles were then able to form atoms. So matter could form in the early universe thanks to a mechanism related to the Higgs boson. Because this is the matter we are all made of, we will not be here without the Higgs boson. But the Higgs boson is also related to the fate of the universe. I'm not going into the details, I don't want to scare you, but it looks like, from what we know, that the universe today is in a state of energy which is not the minimum. So one day could decay to the lowest, not today, a few billion years, okay, so no worry. But the Higgs boson and other elementary particles are related to this mechanism, so it's very important to continue to study the Higgs boson to understand if the universe is stable or metastable. Okay, apart from this question that we have already answered, with the Large Hadron Collider, there are many other open questions in fundamental physics. One, which is of course the obsession not only of particle physics at accelerator like me, but also cosmologies and other astroparticle physics, is the so-called dark universe. So you all know, I guess, that when you look at the sky at night, you see nice planets, stars, and galaxies. What you see is only 5% of what is out there. All the rest is a question mark. Is made of form of energy and matter that we don't know, that do not interact with our instruments, so we deduce their existence from indirect proofs, now very solid proofs, and we call them dark matter, about 25% of the universe, and dark energy, about 70% of the universe. So understanding the dark universe is, of course, an important goal today. So for this reason now, for what concerns accelerator-based particle physics, the community thinks that we need another collider. So this is the Large Hadron Collider, 27 kilometers. This is the project we are studying now, not yet approved. We are at the level of feasibility study. You know, you see that the LHC looks like ridiculous. It's a 90-kilometer ring under Geneva Lake, mostly in Haute-Savoie, which will allow, together with a big step in the technology, to address the open question like the one I mentioned before, with more huge potential to solve, maybe answer them. China wants to do exactly the same thing. So we are in a competition for leadership now with China. So that was the physics. Now I move to the collaboration. CERN was founded in 1954. So this year we turn 70. It was, like today, a very special geopolitical time, just after World War II, and the shifting geopolitical period. Some visionary politicians and scientists, among the scientists I can mention Werner Heisenberg in Germany, Edoardo Amaldi in Italy, Pierre Auger in France, Niels Bohr in Denmark, decided to promote the establishment of a center of scientific excellence in Europe, with two goals. First of all, bring back scientific excellence to Europe. During the war, many scientists had left Europe because of course, of the Jewish persecution, so they were emigrated to the US, to Russia, etc. So Europe did not have many brains left. So this was goal number one. So you see already the very modern view, the fact they understood that the recovery of the continent after the war also goes through large investment in fundamental research. And second, foster collaboration between European countries after the division of the war through science. And again, this very modern view that science is a glue that can connect people in situations of difficult, of geopolitical challenges. 12 European member states signed the founding convention. Today we have almost double. We will double this year because Estonia will become a full member, so 24 member states. But also we have 11 associate member states. The last one to join a few weeks ago, Brazil, is the first country from the Americas, observers, and so on and so forth. So this, I think the founding fathers will be, I'm saying fathers because they were all men at the time, so that's why founding father. But anyway, so the founding fathers will be very proud because, as I will tell at the end, and as I already alluded to, CERN was able to bring back leadership in high energy physics from the United States to Europe, but also this role of geopolitical of glue have expanded beyond Europe and now, of course, also extended to non-European countries. Our budget is 1.2 billion Swiss franc a year. It's a budget of a medium-sized European university, and we have a community of 17,000 people from all over the world. More than 110 nationalities are represented. Of course, the main contingent come from Europe, but we have also people from very advanced in technologies countries like the United States with 2,000 people, Japan, but also we have scientists coming from developing countries, from underserved countries, you see Nigeria, Oman, Palestine, Malaysia, etc. And in this case, our task is capacity building and helping these scientists bring back knowledge to their countries and so reduce the gap. So you see, we have 17,000 scientists, so it's, being able to work all together is a challenge. And CERN has a very successful model, which has allowed these scientists to work together and to build extremely complex instruments. You have seen the accelerator, you have seen the experiments, you have seen the computing infrastructure, and run these big facilities in a very open, and a very effective, at the same time, a very effective way. Open science is one of our core missions. It's enshrined in our funding convention. Of course, today people talk about open science. In 1954, it was not called open science, but the funding convention says all you develop at CERN, your results, and all your developments should be made available to humanity free of charge, and this is open science. So we publish on open access journals, we develop open source software. So you know that the web was developed at CERN in 1989, Tim Berners-Lee was the CERN staff. After the first years of development in 1994, it was made available to everyone at no cost. So we have a population of 17,000 scientists. If you look at the age distribution, the peak is at 27. So it's very young. I'm also here in this peak, and I will not move from this peak. I will stay here forever. We also have tails. Actually, there are also some people in overflow. We have scientists beyond 100-year-olds who still come in the lab. So working at CERN also increase life expectation, which is also good. Now, only a fraction of these people stays in particle physics, less than 30%. Most of them, the young scientists, the young people, go somewhere else, and most of them go to industry. So it's our task to train them for job in STEMs, of course, in science, technology, engineering, and mathematics, but not necessarily in particle physics. And at any given time, we train some 4,500 young people, including physicists, engineers, and technicians of a broad range of technologies, from cryogenics, vacuum, electronics, mechanics, etc. So, oh, sorry, yeah. I am close to the end. We also invest a lot of time and efforts in education and outreach targeting the general public. I think we scientists, we really need to communicate more and better. We are in a period where we see a decline in trust in governments, trust in media, trust in science, and so it's important to continue to engage the public in what we do. CERN has been always very active, but how our scientific and educational activities have been now boosted when we inaugurated last year, in October last year. The Science Gateway is a building complex realized by architect Renzo Piano, which consists of 2 tubes and 3 pavilions. We opened in October 2023, and since then we received 220,000 visitors. We really, between 1,500 and 2,000 people a day, schools, families, etc., and also some special visitors. My last point is technological innovation and impact on society. I told you that we develop many technologies in many fields which find application in several domains of society. So the web, I mentioned the web, but also accelerators to treat cancer with protons and light ions based on certain technology. You see here a wonderful high-resolution, three-dimensional color X-ray of a wrist made with CERN electronics. This picture was published by the New York Times. You see a dosimeter. This is a device to measure radiation on board of the International Space Station. Use of CERN AI and machine learning for autonomous car, driverless cars. Sustainable research and environmental protection is also absolutely important. CERN does a lot. I don't want to go into the details because in the interest of time, but we work a lot on this, in particular also in developing technologies that can help society to defend the planet. And I go to my conclusion. So CERN today is an example of scientific excellence, and we were able to, during 70 years of history, to bring back leadership in particle physics to Europe. There are not so many fields in science and technology where Europe overcomes the United States and China. And this is one. It's a driver of innovation because we need to develop advanced technologies for our instruments, and these technologies are transferred to society and industry at no cost. It's a place where we train the young generation, we attract talents to Europe, so we try to retain talents in Europe, and we train a STEM workforce for industry and other areas. CERN is an example of collaboration across borders, which has cloned then in other institutions like Sesame in the Middle East. But the CERN model for cooperation is now taking as an example. So people talk about a CERN for AI, CERN for quantum, CERN for health, CERN for climate change. So to export it, and we support open science as a means not only of boosting science, but also to reducing inequities across the world and reduce the gap between the poor and the rich, people from low and people from high-income countries, those with and those without access to knowledge. So CERN is not only a big European success, but is also a value system, and I'm happy that Professor Loprieno mentioned this in his introduction. But let me finish with science, because of course I'm a physicist, and this is what really what I like. So this is a beautiful image taken by the James Webb Space Telescope. It's a beautiful image of the sky. And of course, when we look at those images, our eyes are attracted by the luminous object, by the stars, the planets, the galaxy. They are fantastic. But for us, particle physicists, what is important is the dark and the vacuum. Today, we don't understand the dark. We don't understand the dark universe. We don't understand what is in the dark. And we don't understand the vacuum. The vacuum is not empty in physics. It's full of energy. It's full of particles that pop in and out. We don't understand its structure. It's related to the expansion of the universe. It's related to the fate of the universe. So the dark and the vacuum are the next frontiers in fundamental physics. Thanks.